Yeah, thanks for coming along. We thought we'd do it this way. I give a very, very brief introduction what GeNN is in general with a bit of history, literally 10 minutes or so. And then Jamie's going to take over and walk through the live demo in the repo and so on, as we did it last time, which worked very well. So in terms of introduction, we're going to talk about GeNN. GeNN was originally invented by myself, and then these other people who are the main developers joined. James Turner, Esin Yavuz did it for a while, and then Jamie joined about 4 years ago and has been the most active person since then. And then we had a few project people in, so I wanted to acknowledge them all who did parts and bits of this. We'll come to what these parts and bits are in a moment. Now, so what's GeNN about? When I got to learn about CUDA was when the first CUDA versions came out. I thought it's exciting. We had a GPU, and so I hand-coded a model on CUDA, and it took me a long time and was quite painful. But the results were promising, so I just showed a slide. I won't go into any of the details, but all that's shown here is like the different speed-ups I could get for different parts of the model.
Thomas, we can't see your slides. You're sharing the presentation, not the, you're sharing PowerPoint, not the presentation.
Oh, that's funny. Was that possible? Let's try this again. I mean, I might as well just share my screen then.
I think it generally has an option to flip which one is being shared, whether the full presentation or the PowerPoint window.
Well, what happens if I do this?
Yeah, now we can see your full slides.
All right. Strange. But I guess I shouldn't have changed to the presentation mode while it was sharing already. That's also something to learn. Okay. So there we go. I was on this slide one further down. Yeah. So and so what I was saying was basically it was promising. Overall, I got 24 times speed up. I was quite happy, but it turned out that I had to make very specific choices. They were very specific to this particular model and the particular GPU I had. And you appreciate what the problem is if you just think about what CUDA does. Yeah, it abstracts away some of the hardware specifics and gives you this kind of interface where you're thinking in blocks and threads and so on. But it turns out to get good performance, you still need to worry a lot about optimal block sizes, and that depends on what GPU you have, and you need to make your memory access coalesced, which simply means that threads that are adjacent in terms of their execution also need to go to adjacent memory when they access memory for it to be efficient, these kind of things. So you have to worry a lot about what's actually happening in the background. And then if you think about what the neural network simulation does, then you see immediately that it's a lot of bean counting involved in that, because you have neurons, they come in populations, they don't come in grids and blocks. Yeah, so you need to kind of map it all onto each other. And while that's pretty trivial, it's a lot of kind of bean counting work that no one wants to do. It's really boring and takes a lot of time and is error prone. And that's why GeNN was invented. Yeah, so the approach there has always been, and it's still to date really, that we let our users, and when we use it ourselves, obviously ourselves, define all the model, the equations, what the network is, how it all works. It's all defined by the user, and GeNN does the bean counting, and generates these kernels for CUDA and maps it all onto blocks and threads and worries about coalescence of the memory and all of that. So we have GeNN for that, and that's it. And the user controls all the rest. So it's not like a bells and whistle full-fledged simulator that way, that it gives you all kinds of graphical interfaces or anything like that. No, it's just for getting rid of this nasty bean counting problem to get CUDA code efficient. And that's all I want to say about the origins. And then fast forward to today. Since then, we have developed a lot of convenience around this. So the original GeNN was in C++ and still is in the middle here. And then on it, we have built now interface to other things people like. So for example, with Marcel, we have built the Brian to GeNN interface so that Brian code can be run through GeNN on a GPU. We have developed our own Pine interface through what we call PyGen, which is a Python wrapper for GeNN itself. And we even have in development something now where you can translate machine learning models that were formulated in TensorFlow into spiky neural network models in so-called MLGen, and then use the GPUs to make that efficient. And we have the spine creator thing. Probably no one really cares about this. It's a very specific thing of one of our collaborators that wanted that. It's an XML based format, really, the spine ML. Okay, and so that's how it looks today. And so there is a lot of convenience built around the core GeNN, but still the principles are intact. You will see the examples. You have full control of everything, your model code and how the network looks like, how you do the I/O and so on. It's all left to the users. And some people might think of it as a burden, but I think of it as an opportunity. Yeah. Okay, and then just to show you a little bit what it can do. So this is work from Jamie. He's coded this cortical microcircuit model, which is a good sizable model. It's 80,000 live neurons with about 300 million synapses. And then it was run on the benchmark, as a benchmark on HPC and Spinnaker. That was a different paper that is cited down here. And we tested it on GeNN. And if you look at the comparison, it looks like this. So this is updated actually from the paper. The original paper is here. But we have updated to today's GeNN and today's latest GPU we have. And then you see the comparisons like this, also to the most modern Spinnaker. And you can see that like Spinnaker beats the HPC now. That wasn't the case in the original paper, but they have updated their software stack and it's much better now. So they run at real time, and the Titan RTX GPU can now run it on less than real time. So we're again the fastest in the game for a while, and then they will do something new, and the race begins anew. That's one example. And then the other one I want to show is we can also do really large models. So this one is using this microcircuit model as a building block, and then uses the macaque connectivity that comes from a tracing database, the so-called COCOMAC database, and then builds a big visual cortex model, so to speak, from these little patches of cortex. And so this one's quite big, yeah. So that has about 4 million neurons and 24 billion synapses. And if you want to just stick it on a GPU with our previous methods, it would be a bit difficult because you need memory of about 180 gigabytes just to store the connectivity matrices. And so Jamie rediscovered this really fun trick from Itzikevich. He used it already in 2006 to model a thalamocortical model of the size of a human brain on a modest computer cluster, which quite an accomplishment there. And the idea is you actually don't store any connectivity matrices, but you dice them out whenever you need to know whether there's a synapse or not. So this picture doesn't really say much. It just means that you have a procedure for finding out whether there's a connection. You don't read it from memory, and you never store any connectivity in memory. And as long as you're not learning, that's a valid approach. Yeah? If it's based on a random number generator and some sort of mapping for the weights, then you can redo that at any time you need it. And interestingly, on GPUs, this is quite efficient. Yeah? And so we can run this huge model on a single GPU now, and it's quite it's okay fast. Yeah, so 7 minutes for biological second compares to a couple of minutes, I think, on the newer Jülich supercomputers per biological second. So it's a bit slower, but not much. But they're having a full supercomputer rack to run it. Okay, and I'm not going to talk more about this. I mean, this is just verifying that we get the same results. Okay, and that's the last thing. Just wanted to show a couple of symbols here from funders. Yeah, so this has been funded over the years from very different sources. Most recently from the EPSRC, who pays Jamie in all his works on the so-called Brains on Board project. And that's all for me, and I'll hand over to Jamie at this point. Of course, also happy for people to interrupt and ask questions. I should have said in the beginning, and Jamie's the same, obviously.
Yeah, so this is going to be my first time doing an interactive dev session. So if anyone has any questions or if anything doesn't make sense, please say. The first thing is, can you all see my screen? Or at least, can anyone see my screen? Excellent.
Yeah, good.
So let's start by looking at the GeNN GitHub. This is very much inspired by Marcel's dev session a few weeks ago, but I fear this is going to be less practiced. So we've got a GitHub organization for all the GeNN projects. So as Thomas was saying, we've got this ML-GeNN project more recently for interfacing with TensorFlow, and we've got PineGeNN, which is a Pine interface that sits on top of GeNN itself. one of the things people have been talking about in these sessions is having some kind of having discourse or GitHub discussions for kind of not quite issue level questions from users. And I think that's something we really need to start doing, because we have a lot of sort of issues that are, I can't run Gen, blah blah blah, and you try and close them because they mess up your issues, but then some next person that has that same problem can't find it. So we're sort of looking for a solution to that ideally works at a kind of GitHub organization level, so it can cover all of these things. And it doesn't seem like GitHub discussions is quite there yet, which is a shame. But anyway, so these other libraries are in various stages of development, but I'm mostly going to be talking about GeNN itself here today. As Thomas said, GeNN remains 84% C++. So the sort of layer of Python on top is fairly slim, and we have various kind of modern stuff hooked up to it. So we have full code coverage using CodeCov, which is really cool, and it's yeah, I'll come back to that actually when I talk about testing in general. But the so this, yeah, there's not really much point going through the code here. We also have slightly old school, I know now, but we have Doxygen based documentation for GeNN. This has historically been only C++, but we've done various bits of HTML hacking and plugins, so it documents both it documents the C++ and the Python APIs. So if you go into the namespaces, for example, somewhere in here you see the Python, and we've got some plugin that translates PyDoc to Doxygen. So for example, you can see hopefully reasonably documented Python methods, as well as the C++ stuff. So the idea is that the idea is that the Python interface is very similar to the C++ interface. So there's a sort of, we don't want to do everything twice in two different formats, and we want sort of stuff to be available to both in the same places. So in the documentation, for example, there's separate tutorials for Python and C++. But then in other places, we've got this, which we stole from OpenCV. So you can switch between Python and C++ views of the same documentation. So the documentation is reasonably complete. As with all these projects, it's an ongoing fight to keep it up to date. I sort of had a purge on this a few weeks ago, which I think has really improved the situation. So I'm going to start sort of this hands-on bit by showing how you actually use GeNN in its sort of classic C++ form, because I think it's informative. And as Thomas says, I think the kind of low levelness remains a feature rather than purely being a bug or a sort of legacy thing. So, this is what so you're in C++, your GeNN model typically consists of two parts: a model definition, which purely defines the structure of the model, and then you have your own simulation loop, which you link against it. So this is a sort of traditional classic model definition. What this model is going to do is show off 4 regimes of an Izakevich neuron. So the way the C++ interface to GeNN basically works is GeNN itself is a static library, as are each of these backends that Thomas showed in the diagram. So there's one backend that generates CUDA, one that generates OpenCL, and one that generates sort of very basic C++ code for running on a CPU. So what the GeNN command line tool essentially does is link this model definition against those 2 libraries and run the resultant code, which generates the GeNN code. So we can do this now. So we do GeNN build model, and you can see it's compiling. So on CUDA, as Thomas was saying, GeNN tries to do some optimizations to make the model better fit the particular GPU. So it tries to maximize occupancy and stuff like that. But once it's done, you get a directory like this, which will be full of CUDA code. In this case, we've got a kernel to update the neurons, and this runner module, which basically contains the code that launches the kernels. So with this command line tool, you can also generate CPU code. So if you -C, you get CPU code. And the idea is that these different sorts of code generation, they can all be linked against the same simulation loop. So if I do CPU or OpenCL, the same simulation loop will work. So in this model definition, you get given a model spec object, which you have to configure. So you set a time step, you give it a name, and then you can define your neuron and synapse populations. In this case, we've just got a population of 4 neurons, 4 Izakevich neurons, and we're driving in with a DC current, so they actually do something. This is the kind of syntax that you define your GeNN model in. And then you link it against a simulation loop. So this again is pretty basic stuff. So you call some pre-generated functions to allocate the memory. All of the GeNN memory, all the CUDA memory GeNN uses is statically allocated, so there's no kind of dynamic runtime allocations or anything. And in this case, if in the model we set some of these variables to be uninitialized, this is because we want to set the different neurons in the population to have different parameters at runtime, so we can see the different Izakevich regime, the different regimes of the neurons. So we set these here, and then we call the kind of second part of the initialization, which actually uploads those to the GPU. And then again, going back to the thing Thomas was talking about, we do our own I/O. So we simply open a text CSV file, and in our simulation loop, we call step time, which advances the state of the GeNN simulation. We call this pull function, which copies some data from memory. And we write the voltage of the 4 neurons to a text stream. So if we go to this project, right, so again, here we are in our. So now we're linking the simulation loop against this thing, and I suspect this run already because it's very quick, or else Windows is being very slow. Either is possible. Yeah, so it's made the output file, yeah. And now we can run a little plotting script to show what our output looks like. And lo and behold, we've got our 4 Izakevich neurons. So that's kind of the user experience of using GeNN for using GeNN from C++. And this, you might think that this is kind of irrelevant. Everyone wants to use Python for this type of work, but there's lots of things that where you really want the kind of low level access to the spiking neural network model, incorporate into your own thing. So we've done this quite a lot on robots, which is clearly a bit harder to show on a Zoom call, but it's also good for kind of hooking into your own simulations. So this is something we've actually done for the Brains on Board project. So this is a kind of model of ant navigation, which is using a GeNN spiking neural network model as kind of the central brains of it, and an OpenGL visualization framework around it. So what we just did was we trained this little spiking neural network on views of this route as this agent travels through the world. So this process snapshot is the kind of view it gets of the world. These are sort of the latest spike rasters of the model as it goes along. And now we can test it. So this is the agent going along and looking for the best view along this route. So this is the kind of thing that's really easy to do with GeNN. Like anything you can do in C++, you can link GeNN, and you can link a GeNN model into it and add spiking neural network AI, which is pretty cool. But nonetheless, Python is clearly here to stay in the world of computational neuroscience. So as Thomas was saying, we've been working on this PyGen interface for quite a while, and the aim of PyGen is to kind of keep the same spirit of being able to control everything yourself, but make the API to do it a bit more Pythonic and a bit easier to use. and where possible, keep the performance as good as possible. So this is the same example coded in PyGen, and you can see that instead of sort of having to order your parameters correctly, as we did in the C++ one, we've got dictionaries for configuring all this stuff, and you can see that the variables that we initialize at build time and run time are all in one place, and they're all just, the syntax is exactly the same. Otherwise, the syntax is quite similar. So we call these add neuron population type functions, and we call build and load. So build actually does the code generation, load then loads the generated model into Python. And again, we specify our simulation loop manually. So we loop through the model's time for 200 milliseconds. But because it's in Python, we don't need to save this to a CSV. We can just get the data straight into a Numpy array and plot it, which is really nice. The other thing to note is that we use these Numpy Views, which basically give you a view into the C++ allocated memory. So this V view here. This is actually pointing directly to the memory allocated by GeNN. So there's no copying going on when we do this. So you can access the sort of underlying data without copying, which is really nice. And it means that if you're careful with Numpy, you can get very good performance, even if you're having to do some limited Python processing in the loop. So if I run the Python version, you'll see that very similar things happen. It does the code generation, and the generated code will probably look very similar. Put in some CUDA. And the same thing, same result occurs. So that's basically how you use GeNN from Python and from C++. I'm going to sort of go a little bit deeper into the C++ and then the Python. So following the general structure we were talking about in Thomas's part of this talk, the GeNN project is built as 4 libraries. There's one library for GeNN itself, and then there's extra backend libraries for CUDA, OpenCL, and the single-threaded CPU. The GeNN project itself both defines the interface that you're messing with in your model file. So this model spec class is kind of the heart of it. And then there's different classes for groups of neurons and populations of synapses, all that type of thing. And as well as that, there's sort of generic code generation built into the GeNN library itself. So the ability to make files and MS build projects for Windows, and the kind of generic logic for generating code. So obviously this is not the best way of doing this, but this is kind of a typical bit of code generation code. This is the code that generates neuron update kernels for whatever backend you happen to be using. So this function, you first of all call into the backend, which will generate kind of the framework around the generic code. So this will generate the CUDA kernels or the OpenCL kernels, and then it will call back into this generic code here and generate the actual the code within that, which remains the same. So this sort of approach has meant that we can keep a lot of the code generic and add new backends with a sort of minimal amount of effort. And there's a kind of additional layer of abstraction that we found that we initially implemented the OpenCL and the CUDA backends totally separately, where we ended up finding that there was a vast amount of overlap between them. Like, apart from the actual details of how you define kernels, the actual algorithms are exactly the same. So the algorithms are now generated at this, or now defined at this kind of generic single instruction, multiple threads level. So for example, let's just find a arbitrary algorithm here. Right. So this is one of the algorithms we use for generating synapse code. So the majority of this is generic across OpenCL and CUDA, but then we can then sort of call specialized functions to generate a shared memory barrier, for example, or put data in, or sort of generate a variable in the shared memory rather than the global memory. That type of abstraction. But beyond that, these backends can be treated very similarly, which is really nice. I think that's probably enough looking at codes for now. So to wrap, the only bit of this that really needs exposing to Python is the sort of front end aspect, which is the model spec class that you're interfacing with here, and the individual neuron populations, because these functions return neuron group objects, which you can then set further stuff on. So the classes that they return and the model spec need to be exposed to Python, but not a great deal else. And we wanted to do this in a way that required the sort of minimal updating. So if we added a new model to GeNN itself, then we didn't want to have to manually update the Python wrapper. So for better or worse, we chose to use Swig for this, which is a kind of generic, it's a tool for making bindings to high-level languages from C++. So it's in fact very generic. So theoretically, we could make a Perl wrapper for GeNN if we pathologically felt the need to do so. And this, this was initially a student's work, so there's some bits here that need a little bit of tidying up to this day. But we have a kind of, let's just see. Yeah, so you have these interface files which kind of join together the bits of C++ that you want to wrap in one place. And this defines what the Python interface looks like, essentially. And this handles how you wrap things like templates that you can't expose to Python directly. It kind of expands templated C++ into multiple different Python classes and all this jazz. And this sort of handwritten Swig interface are combined with sort of auto-generated Swig interfaces, which is the bit where it gets a little bit sketchy overall. So this script, which is our students' work, basically passes a whole bunch of GeNN and finds different sorts of neuron model and builds the Swig templates for them automatically. So this seems a bit delicate and often sort of breaks in unexpected ways. So I think at some point in the future we're going to move away from this approach in Swig. But for now, this is how we build our wrapper. The problem with Swig is that the sort of results don't necessarily look very much like Python. So you have to put your data in these weird Swig containers rather than like lists or Numpy arrays. So on top of this, we've got a very thin layer of Python. So we've got basically these three files. We've got this the GeNN model, which provides kind of a thin Python-y wrapper over the model spec, and various Python groups. So the neuron group and the synapse group, which again provide a very thin wrapper over the different group classes. And these are what provides this dictionary function and various other stuff. And the cool thing with PyGen is it lets you define models, sort of new neuron model types within Python. So you don't have to change GeNN itself to add a new neuron model. You can define them inline in Python. Though slight oversight, I don't think I actually have any syntax demonstrating that. Let's see. So yeah, for example, this is a very minimal custom neuron class here, and you can create that entirely within Python. So you provide basically lists of the parameters and the variables, and then you can provide this C-like code, which currently gets pretty much passed directly to the compiler, but at some point in the future we're going to maybe start parsing. And this then builds a Python derived class off the C++ class, and everything else works as before. So I think this is a really unique feature in GeNN, that you can define your models in the same script in Python without having to delve deeper. So I think that's probably enough code for now. So talk a bit about the testing that we do. So we have two main types of tests. So we have unit tests, which are kind of typically covering more recent parts of the code. So all of our tests use Google tests, the Google test framework. When we started doing that, that seemed the best choice. Most of these are very simple Google tests, so they're sort of testing bits of sort of gnarly logic. So for example, here we're making a neuron population, giving it some parameters, and we're checking that it correctly detects that this population needs a random number generator, this type of stuff. And these are really cool, really fast to run, and they're good for kind of coverage of corner cases. And I'm sort of getting into the habit of writing them as I develop new features, which is clearly what one should do as in test-driven development. Also, for any Windows users, the Visual Studio integration with this is really nice. So as well as these, we also have, we call them feature tests, but essentially they're integration tests. And these are rather older, so some of these go back quite a way in one form or another. And there's quite a lot of them, possibly more than there should be. And these consist of sort of very small GeNN models which test some particular feature. So, for example, these decode matrix tests, these are testing basically that different types of synaptic matrix work. So they tend to do something like sort of binary coded decimal decoding using binary weights or something. So the synaptic weight matrix has some kind of deterministic function. So you feed spikes into it, and you know what the pattern that comes out should be. And we use these to test that the code generation works. And these are, because it's very hard to, because a lot of the code generation is somewhat monolithic in that it's not necessarily clear how you could test it in a more modular way. So if you apart from sort of examining the code in your test through some regular expressions or something, it's not really clear how you would test that the generated code is correct. So we aim to do that by sort of covering permutations of features and running them against all the backends on real hardware. Which brings me to the next tricky part of this. The unit tests, the idea is that they don't really use any backends. They don't get as far as generating code by and large. And if they do, they use a CPU backend that's kind of a mock. But these tests, they really need to actually test the real backend code. So this has made doing this sort of online tricky, because to our knowledge, none of the kind of commercial, at least none of the free CI services offer CUDA nodes. So we had to sort of roll our own solution to this, because we can't really afford to be running Amazon Web Services instances with GPUs whenever we want to push a commit. So I've got a little diagram here. So we've assembled this. Where's it gone? That one probably. We've assembled this sort of network solution. So this glorious diagram. So this side here is the internet. Oh, damn, that's the internet. And here we have GitHub, and this is communicating with a server which we have that sits with one network interface on the internet and one inside the Sussex firewall. So this is really getting in the way of this thing. Thanks, Thomas. So this is the one that's running our Jenkins server. So this is the heart of our testing. And you can see it's running this project and a Brains on Boards organization. And within this, we're we're testing all the projects in Gen. The angry cloud is not representative. I think it's just a few broken branches, but that's, so if we go to master, you can see that this is tracking various things. So we're using the warnings tracking middleware, which tracks the warnings on different compilers, as well as the running of the test results. So if we go to the latest build, which may or may not have been me pushing some fixes to master, but never mind. You can see that there's logs from 3 different devices, and these are actually, so this Jenkins server is communicating with workstations in our offices, basically. So we've all got GPU equipped workstations, and very few of us are using them all the time. And even when we are, a few of those small models running doesn't really do any harm. So this gives us the advantage of testing on different platforms. We've got a Mac. We've even got a Mac with a NVIDIA GPU, which is the rarest of ancient devices. We've got various esoteric Linux distributions that people choose to use, as well as sort of standard Ubuntu with different GPUs. So it's not ideal. I mean, ideally we'd have sort of better balance of GPU versions, but such is life. I think it might be good to switch to some kind of containerized solution instead of relying entirely on the environment of the machines, but for now this works okay. So basically the Jenkins tests run on any machines that are available. So they look to find a list of machines. Oh, actually, I can. So Jenkins is it's clearly designed by the sort of enterprise people that love Java. So it's sort of a bit Java centric, which means using it for C++ is sometimes not as good as it could be. But it's driven by this programming language called Groovy, which is some kind of JVM scripting language. So we have our test system looks to find as many of these permutations of machines as it can. So different CUDA versions, different operating systems. And once it's found machines that match as many of them, machines that match as many of them as possible, it then runs the build on all of these. So in this case, it's found INF 324, which is an Ubuntu machine. Both of these are Ubuntu machines, actually. And this is the infamous Mac with the GPU. And at the end, it also generates wheels of PyGen. So these are binary distributions of PyGen that you can just install really easily. And one of the things we're working on is making the wheel building robust enough that we can actually start putting them on pip, so we can install PyGen much easier, because currently installing it from source is a bit of a pain. And these logs provide the sort of raw output of the build. So you can see that these Google tests are running here. You can see that there's various compiler output, all that kind of stuff. But also the warning middleware tracks warnings. The UI doesn't necessarily work very well, but it tracks warnings and gives you some clues to where they might be. And also it tracks the tests, so you can see all the tests that have run on this. So you can see there's about 1,000 tests typically run on each of these runs. So this is really good for tracking down backend specific bugs or kind of hardware, because you tend to get different bugs on different GPU generations, especially if you're playing a bit fast and loose with the timing. And one other thing that this does is the build process includes codecov for code coverage. So whenever you push, it builds a code coverage report. And this is aggregated across all the machines, which was horrendous to set up, but it seems to work 75% of the time now. And you can see as you go in that you can see the coverage in each file. Like some of these, it's slightly deceptive because these files have got lots of sort of boilerplate in. But for example, if we go here, if we're really lucky, it'll load, and you can see that a whole bunch of these functions are not being hit. So clearly, this module could do a bit more testing, but a lot of places are getting hit lots of times. And you can see here, this would be the kind of place where a unit test would be really good. It's not as well tested as it could be in places, but still, we've got the test coverage up to yeah, up to about 87%, which is, I think, pretty good. And C++, you do have the advantage that the compiler will catch at least some sorts of error. Currently, we don't actually test PyGen itself on top of this, which is clearly a bit of a problem. It's not totally clear how we would do that and not just duplicate the same tests in the same tests we make in C++. Potentially, we could add more unit tests. I think currently our solution is basically to run the Pine, because Pine has its own test suite. We run the Pine test suite on top of PyGen, which at least tests a reasonable part of it. But that's definitely one sort of hole in our testing strategy. Yes, I think that's about what I had planned to say. If anyone has any questions or thoughts, I'd love to hear them.
I got a question.
Awesome.
Do you ever see yourself going away from the code generation plus proprietary compilation step approach?
No, I don't think so. I think it's a reasonably sensible way of generating GPU code. I mean, I think C++ and CUDA compilers are getting better to the point where you could potentially do quite a lot of this stuff through the compiler itself. But I think the code generation is really useful.
How did you arrive at the approach in the first place?
I think that's one for Thomas.
Oh,
Yeah.
okay.
Well, I mean, what can I say? I mean, it seemed the natural thing to do when I tried to get rid of my bean counting was just to replace my own programming actions by some middleware that was doing it for me. It seemed at the time the most simple thing to do, to be honest. Yeah.
Cool. And does it have some unique advantages to compare to other approaches? Or is it mostly like a historic choice and now you coded yourself into a corner?
Okay, what do we say about that? I mean, it gives you a good deal of flexibility what you want to do. In principle, I mean, you can mangle this up in any way you want. However, that being said, we're actually not doing much along those lines. I mean, our code generation is actually quite simplistic in most cases. I don't know, Jamie, you want to say something about my slightly more complicated issues like different parallelization strategies? Or
I mean, I think one thing that code generation is potentially going to give us an advantage in the future is that we can start parsing the code that we're given and apply kind of domain specific optimizations that would be tricky for a standard compiler to do. And we don't currently do that, but that's something we could do. And similarly, we could after we've parsed the sort of code snippets, we could omit code for something that doesn't let you program it easily in C. So FPGAs, that type of thing. Or we could generate SIMD code for like intrinsics for AVX 512 or something like that.
Makes sense, yeah.
But I think there's less when CUDA was much newer. I mean, Thomas started using CUDA when it was basically 1.0. It was C-based, so there was less. You had less of a smart compiler to play with. I mean, potentially now with sort of C++ 20 and the CUDA compiler, you can do much smarter sort of constant expression type stuff than you could do. Because part of the thing you can do with code generation is you can fold your constants and stuff yourself and put them into the compiler, which would be tricky to do in C potentially.
Mm-hmm.
Yeah.
And sorry, go ahead.
Well, I just was about to add, in the very early days, of course, it was quite bare bones. No, you also had the situation where you really had to watch it that there was no checking in the CUDA compiler for anything. So your first indication that you might have done something wrong was that your results was all 0 and you had no clue, what the hell was going on. And then to put your own constraints in to do the right math for the size of your GPU memories and so on seemed the smart way of going about that. Yeah.
So GeNN dates back all the way to CUDA 1?
Yeah, pretty much. I mean, not the actual GeNN, but the hand-coded stuff that preceded it, and then it came from there. 3 years later. So
you didn't have templates in CUDA back then, did you?
No, definitely not.
It was C originally, I think.
It was pretty much C, yeah.
So another thing, to the extent you're allowed to, could you talk a bit about future work? What's in the pipeline? Ideas?
So yeah, I think one thing I'm really interested in is is sort of taking it, because basically what we're trying to do currently is is kind of biologically plausible stuff on a GPU. So we're doing local learning and neuron dynamics, but without talking to other neurons, all this type of stuff, which is cool for computational neuroscience. But the GPU is also really good for less biologically plausible stuff like reductions and all this type of thing. So we're sort of looking to include some more machine learning centric tools into GeNN, so you can take advantage of the fact that it's optimized for spike-based processing, but also do some more machine learning stuff. So gradient-based learning, that type of thing.
Yeah, one other thing we were excited about not too long ago was to kind of break the hold that CUDA had on us, and invent this OpenCL backend. But to be brutally honest, I mean, that was a big disappointment. Jamie can describe it better, but it really did.
3 months of my time I'm not getting back.
Why? What happened?
Basically, there's not really any hardware that supports OpenCL particularly well.
I see.
Apple doesn't. The original idea was it would let Mac users use GeNN better on Macs, but it doesn't. Mac OpenCL drives have been broken for quite a while now. It doesn't look like they're going to be fixed anytime soon.
And then we had some alternative hardware that we thought, with other GPUs and small low-powered microcontrollers, where we thought, oh, this would be really cool to run on there, and then they turned out to be really, really slow compared to the Jetson devices. So it was a bit of a disappointment.
Yeah, I mean, we've still there's quite a few things we'd like to fix to get OpenCL working decently on AMD graphics cards at least, but it doesn't really look like AMD is supporting OpenCL particularly going forward. So it seems like it wasn't necessarily the best plan, but it did at least let us sort of refactor the single instruction multiple threads pathway away from CUDA. So if there's some alternative, it should be relatively easy to target it in future. Like we're looking for a student actually to have a go with ISPC, which is it basically looks like CUDA, but it targets simmed CPUs. So that type of thing, that's going to be made much easier because of the work we did with OpenCL.
And maybe a bit more generally speaking, even outside of GeNN, is there something you'd like to do or see done in the SNN simulation space in general?
Well, I mean, we are quite keen to go in, enter that game of doing bio-inspired SNNs for machine learning. So there's a big space, I think, where we can do more. And our simulators are very biology-centric, I think. So there's a lot to be done to make this useful. And then, I mean, we shall see how it pans out between traditional artificial neural networks and spiking neural networks for machine learning, whether that actually is the new generation and we could be the middleware between the traditional stuff and neuromorphic instantiations in specific hardware, something like that. I mean, that would be, I think, we want to really get into that game as well. So.
Cool. Thanks, guys.
No worries.
Cheers.
Can I maybe ask, so possibly naive question because I don't know much about GPU programming, but what you've showed us today and what I've seen, let's say also for Brian, for example, is the workflow of preparing a network and how the data is handled is often that you define your stuff and then you predefine your data. then you observe the dynamics. However, when I think of machine learning with spiking neural networks, I also think of kind of live data processing kind of approaches, for example, processing a video feed or something like that. And I can imagine that this requires completely different way of managing data and making this fast enough so that you can actually process things at real time, for example. So is there any way you could do that with GeNN, and
I mean,
what are the problems in doing
this
so?
is actually I think this is one of the areas where GeNN actually has a real advantage over, say, Pine, where you're locked into this run for however many time steps type model. Like you're free to use the you're free to write your own simulation, reading video frames and applying SNN processing to them. So I think GeNN's really suited to that. It's currently in the category of things you have to kind of do yourself in C++, but getting data efficiently into GeNN is going to be part of the sort of work on moving into machine learning, I think.
And yeah, and so you can use this anywhere you like. No, the code you're provided with makes you a simulation time step, and you define how large that might be in time. And you could drive this in your own simulation loop, as Jamie says, or you could even drive it by event if you wanted to, and say, okay, now calculate me a time step now, depending on some sort of event or something, right? Of course, there are also limitations. You can't really redefine your network on the fly real quick. I mean, that's a bit limited. I mean, you can change connection strengths. That's no problem at all. And you could define extra connections that are silent at first and activate them, but you can't really redefine completely how it's wired up or the type of a neuron or so, because that's compiled in. So that there it becomes a bit inflexible. But it depends whether that's really something you want to do.
I see. I mean, that already sounds like what I was asking. So, but if you estimate the time required for doing, for a reasonable size of network, one simulation time step versus getting one whole frame of a video feed into the shared memory, or the memory that it needs to be, I don't know which one. What do you think requires more time, actually, the data I/O or the GPU processing?
I mean, you typically want your network to carry on running at real time, so 1 millisecond time steps. If your video's 30 frames a second or whatever, then you'd probably have quite a few spiking neural network time steps for each video time step, I guess. So that's something like the video I showed of the 3D worlds where the GeNN model is running inside it. That's the kind of, you also have those problems there because the world is running at whatever 60 frames a second and the GeNN is running it on a 1 millisecond time step.
Yeah, but I mean, so in terms of what time it takes, it's hard to say. I mean, depending on what GPU you have and what your frame size is, like resolution wise, you will need some time to copy it in and out. And yeah, as you said, it typically would go into the global memory of the GPU, and would be then accessed from there. And you need to make that transfer. The bandwidth is quite high on these. I don't recall any recent numbers. Jamie, what is it? Do you remember? It's higher than what you normally have in I/O. Yeah, so it's quite good. But of course, it's a bottleneck if you really want to stream stuff on a quick basis. And there's also some latency, obviously.
Yeah, and the higher end cards tend to have kind of DMA controllers, so you can do the copying while you're running the model. So it's not, the GPU itself isn't kind of hung up doing yeah, exactly. But yeah, it's a silly unit. But here we go. Yeah, so we're talking kind of 700 gigabytes a second of bandwidth. So there's no shortage of bandwidth.
Then the latency would be the other question, right?
Yeah,
but I think if it's really 60 hertz or so, then it wouldn't be a problem compared to, as Jamie pointed out, the model running much faster. Yeah. So yeah, no, this is something we really like to do. That's why it's good for the robots, because you can have your real-time signals and you just push them in there, and because your own program is controlling everything, you don't need to worry about some loop running somewhere that you need to connect to, because you're making it. Yeah, so you have full control what you're doing, when and how. Yeah, so you can just plug it in there when you want. That's why we like it. Yeah, actually, and yeah, so the robotic stuff is also I think, a strong area still, and we will continue developing that. So besides the machine learning things, robotics, putting spiky neural network models as controllers of mobile robots. And then at the moment we're worrying much about navigation based on visual navigation. That will continue at least a few years, and then we see where we get.
Because you can get these, I'm using my prop again, Thomas. You
Yeah,
can get these little Jetson GPUs, which, so this is the latest ones. It's the Jetson Nano NX or something. And it's got 6 ARM cores and a relatively powerful GPU. So you can do quite a lot of stuff. You can run quite big models on that in real time. And they've also got the advantage that their memory is set up, so it's really optimized for getting data from cameras into the memory. So that's even faster on these devices. But still, they are only kind of small ARM cores and they haven't got that much memory. So there's another reason why using C++ is potentially a good idea.
Yeah, but we've strapped them onto quadcopters and flown them around. I mean, yeah, the collaborators have actually. We never strapped it on, but yeah, as a proof of concept, it's a fun thing to do. Yeah, just with some rubber more or less. Yeah, you strap it on the back and you connect the power to the main batteries of the quadcopter, and off you go, and can control it by Wi-Fi. Yeah, so it's quite nice. So yeah, there's a lot to be done in that space, and then you can think about applications. Obviously, Andy, our colleague, he's into agri-tech. He wants to put this onto kind of smaller robots to inspect plants and have them drive around autonomously, making their own way, through a farm and finding out what the crops are doing, that kind of stuff. Yeah. Right.
Thank you so much. That was a great presentation. Your documentation looks fantastic. You set a high bar. Yeah, thank you.
Thank
you. Because I was the last time we spoke, we were discussing Gen for NeuroFedora. So I need to buy myself a GPU pretty much to work on that. Does your documentation, by any chance, have a list of cheap GPUs that you can buy or something of the sort?
I can recommend, it's like, I can't remember what it's called. It's like a GeForce 1650. It's really cheap and it fits in the crappiest university desktop, which has got a really small power supply.
Well, because my desktop is a crap university desktop.
So that's exactly what it's chosen for. And if you saw it on Thomas's slide, it's actually really, really fast. Unless the Bitcoin mining world has gone insane again, it's less than €100.
That'll be great, yeah. Because the workstation I have is from university, from my PhD days, so I think it's 6 years old now. So I'm going to have to find a way of fitting it in there somehow.
And the main constraint is typically, either space or definitely the power supply. That's the main thing.
Yeah, that's why that card's good. It's only 75 watts, so it shouldn't need a beastly power supply.
Great, I will look into that. Thanks.
Good.
Any more questions?
Comments? Complaints? Cool.